this login method basically just like binary decomp and you check it?
I need this log the operation for famous little cylinder. So as I will describe why it is needed.
Yeah.
You'll bring it here closer to this direction.
Okay.
Move this in.
So
You take it to the power.
Sorry,
of...
move the whiteboard to the side so you don't disturb the people there.
Wait, can I guess? Can I guess?
Yeah.
You do repeated squaring on the number, and you do it up to like p minus 2 or whatever.
Yeah.
And if it doesn't equal itself at the beginning or something like this, then it is 0. Is that correct?
It's almost equal. So we compute the power of p minus 1.
Yeah.
And this will be 0 if there are given a or the best number is 0, and
Right.
it will be 1
if
this
it's
is
not
not
0.
0. So we use that for converting some number to 0 or 1.
Yeah, got it. Nice.
Wait, ChatGPT came up with that?
Yes.
Holy fuck. What the shit?
So it is described in Japanese, but
Okay, well.
Math is like so it says so I want to compute the function like if a is 1, it outputs 1, but if a is not 1, it outputs 0, and it says we can use this relation.
Oh my god,
Yeah.
it just cited Fermat's little
Yeah.
theorem. Oh my god. We're all fucks.
Yeah, I'm very surprised.
Okay, so then,
Yeah, okay. So
we need to figure out a better way of doing
yeah,
this.
so our definition of the problem is so we want to compute so in the R1CS given their coefficients vectors A B and C and the witness vector omega we want to compute their distillation.
What is this bar?
This means vector because this is not just a number, it's a vector.
Oh, I've never seen this in
You don't put the arrow on top.
Yeah. For us, it's usually like this.
Yeah.
That's fine though. This
Yeah,
works. I can do this. Is fine. Okay.
Oh, you're using a Sharpie? Uh-oh.
Oh no.
Oh.
It's fine. It's fine. Just
Yeah.
get another marker and write over it.
Yeah.
Let me see. It's the permanent marker.
Oh god. It's fine. We can do this. That's a good thing we corrected the vector thing.
I know. What is this one? Is it also permanent?
It's not. Oh. No.
Oh, okay.
Such a beautiful trick of the universe that this works.
Most people don't know this one.
Yeah. Maybe not enough mathematics.
I think it's better to as fast as possible.
No. This is gonna be better. Watch. Yeah.
Okay.
Try now.
Okay.
No. Just use this.
Oh, I see.
Where? It's right over these guys.
Oh.
Yeah, I've done this before.
Yeah.
Here, let's just use this. Disaster averted.
Thank you very much.
Okay,
Yeah.
use this one.
Yeah. Okay.
Let's
So
delete that permanent marker from.
And this is the vectors A, B, and C, and witness vector omega. And we want to check the equation, right? And we can easily compute the bound like.
So A isn't a vector here?
It's a vector. All of them are vector, and it's a coefficient vector of the R. One constant of the R.
Why are A and C different?
Yeah. Why is B a vector and C is C? Oh, this is a line.
The
here.
line inside.
Okay.
Yeah.
Yes.
Let's use the other. This is too much.
Yeah, let's use the arrow on top.
Okay. I think
One more time.
it's
Yes.
okay.
Yes.
Okay.
Thank you. America.
Yeah, I sometimes see this one, and so others are we reject this equation and we can compute which. So for example, z equal or
I cannot believe ChatGPT came up with Fermat's last theorem. That's insane. Sorry, not last, but little.
so we can easily compute this value, and
Right.
we want to say, or we want to make a
Verify
function.
that all of these guys are 0, basically.
Yeah, so it will what if that equal 0 and 0 otherwise. So we want to compute.
Wait, sorry. Just do this. Like, input a random linear combination, like r,
Yeah.
r squared, r cubed, dot, 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 r to the p.
Yeah, we can use random
Multiply
linear
that.
combination, but to do that, we have to consider how to prepare such randomness.
Right.
Maybe challenge can be used.
From the there's no verify. Oh. But it needs to be inside the ZK circuit, right?
Yeah. So if we modify the ZKB protocol itself, so for example, we can increase the number of rounds and using the challenge value as a randomness of the random linear combination, and later the prover also makes some commitment to prove this random linear combination. But I first want to consider whether we can represent the computation efficiently only on the addition and multiplication ends.
Sure. Yeah.
And
But this works, right? And this is more
Yeah, yeah.
efficient than using Fermat's last theorem, little theorem.
yeah,
like,
I think so. So,
that many times. Okay.
so basically, the way that the ChatGPT will show that if that can be so over z or p is a prime, then it can be 1 minus z p minus 4 because if z equals 0, it should be 1, and otherwise from the famous radial cell it will be 1 in all ways. If z is not 0, so it will be 0.
Yep.
But one and one problem is to compute this belt over the circuit, we need at least log 2 p minus 1 multiplication, which is which has a lot of cost.
256.
Yeah, and we have to compute that one for each constraint. So I want to make more efficient solution, like we only need to compute this one in batch only once for all constraints, or we can avoid this a lot of multiplications. So this is the current problem.
So the RLC where you you find some randomness,
Yes.
which I feel like you can get from the commitments, right? Because there already is some Fiat-Chimere you're doing, to figure out which pair of openings you're gonna make, right? Or like there's
Yeah.
already sort of a Fiat-Chimere thing going on. Can't you just like add a 1 and like hash, or you can just make another random value and then have those all be like public inputs where you just
Yeah.
multiply against z, and then you just do this check at the very end that
Yeah,
like the
yeah.
variable from the sum of all those is 0.
Yeah, so if we have some randomness, for example, so if there were z2 and zn, or we compute, so I think maybe consider for example, if defined.
You're gonna double the number of constraints though. Is that fine? That's probably fine.
So basically, addition is very cheap in the second group.
Yep.
But multiplication is only action list.
Is what?
So multiplication is just not free operation.
I
Not
see.
free means it requires the other party's views, and you need to send that views data in the proof data.
Mm.
But in addition, the verifier can compute its addition results only from
With
the
one view.
minimum data. Yeah.
I see.
From self-building. And if we use random linear combination, we can represent this function like z1 plus out z2 plus r down and
Yep,
it
exactly.
works because if any z is not zero, this one should be also not zero with high probability.
Yep.
And this will be zero.
Yep.
And if all zero z is zero, this should be zero, and it will be one.
Yep.
So I think
Yep. How do we do this?
Sorry, so 1 to n means like the 218 evaluations, or
It's the like every single constraint you create a z for it essentially.
yeah. So we consider n constraints, and we compute this z for each constraint, and finally you want
well, I thought the vectors ABCW were usually over the entire circuit, right?
so this vector size is
Have
the
another marker. You can keep going.
yeah.
So I
Ah,
thought
yeah.
the vector size is the size of the circuit.
It's the vector size of ABC. Omega is the number of variables in the R1CS.
Right.
And this equation exists with different ABC coefficients for each constraint.
So this is basically evaluating this polynomial with these coefficients at R.
Yeah.
Is there anything we can do to make that faster inside of the circuit? Or like I guess, so what we're trying to optimize for is as many additions as possible
Yeah.
and not multiplications, because multiplications increases the proof size.
Yes, and
Does it
computation
increase?
course, because
Okay.
for each multiplication, the proof and the verifier needed to compute the Poseidon hash.
Ah.
Yeah.
Proven
Sorry, I'm
or-
super confusing. Grot 16 and the ABC are coefficients of the constraint. So like the first row of ABCW is their first constraint, right?
Yeah.
So I'm confused what's happening here. How's this different?
So okay, so basically here I can try explaining so I can
Yeah.
see if I understand this. Like ABC are indeed like the same exact constraints as you have in R1CS, but in this case like we need to also verify that essentially like every single constraint actually properly equals 0.
So for each row.
For each row, it's
Yes.
like like
So
each
this
constraint.
Is not a full dot product then. This is not a full inner product. This is inner product over only the first row or something.
This is Hadamard product. I guess yeah, this should be this or something, right? Whatever.
It's just a
Oh.
multiplication of two integers because it's an inner product.
Yeah, but I'm saying
Yeah.
the inner product. If you're putting coefficients, if you're putting whatever these sub numbers on the z, then this is not a full inner product. It's an inner product only of the first row or whatever, the first value in the vector. Right, or what is z1?
So it means it is a representation of this equation, and this means inner product of two vectors. So this one is just one integer, and
So
this
it's like,
one
what is z1?
z1. So z1 means z for the first constraint. So this coefficient is
got it.
different for each row, each constraint. ABC vectors are different for each constraint. So this z is defined for each row, each constraint.
So this is the normal like
Yeah.
R1CS, right? So we just take like the top
Row of this,
Yeah.
or yeah, row of this, and then we like pull it out, and that's what forms this thing. Like you have one of these equations for every single row of each of these
Yes.
matrices.
Right. Okay.
Okay, so it seems like this is going to be very multiplication intensive. Like you're
Yeah.
going to do at least n multiplications to be able to get to this.
Yeah.
So this seems not good. So we need to find something that's better, but uses more additions. Yeah, I feel like there's something here, some trick you can do where, because this is just an evaluation of this polynomial at these coefficients,
Yeah.
where you can maybe figure that out with just like additions or something. I don't know. That doesn't really make sense. So I guess like a normal ZK Boolean, like you're just operating everything as like a Boolean circuit basically.
Not Gabriel here.
Boolean.
Boolean error. ZKB works over arbitrary finite rate.
Right, but
Yeah.
in the other implementations of it, like
They're working on binary field. Yeah.
exactly, you're working on like Z2.
Yeah.
So like this check is trivial basically.
Yeah.
If something is 1 or 0. So this only matters when you're entering fields of much larger size, because you need to also verify that these things equal 0. I guess this is definitely better than doing this on every single
Yeah.
one, right?
Yeah.
Because this is n log n, or n log n times log
N
p,
times log to b.
whereas this is
Yeah.
like n plus log p.
Yeah. Yes. So I think in the ZKB side, we can directly output each set, or we can directly output each set as a public output
Oh,
of
yeah.
ZK proof. And in the recursion side, we can compute this ratio.
Oh, yeah. Oh, yeah, let's just
so
do
we
that.
we don't have to modify the ZK protocol itself.
Oh yeah, that's
Yeah.
super easy.
And so
Wait, sorry, but I thought Nova is not hiding, so how if you output the value of Z and it's more than 0.
but I think for
The
honest
information.
honest proof, it
It'll
should be
always be
0.
zero.
Oh, it's always
Yeah.
0, right.
Yeah. So we don't have to protect the privacy against malicious proven.
Right, yeah,
Yeah.
and Nova. So in the folding circuit, you just have like an extra n constraints basically that does this like RLC, and you just check that it equals 0.
So
Yeah, that seems fine.
yeah. So I think the challenge value of the ZK protocol can be used as a L.
Yeah.
And next, in the recursion circuit,
That's one of the inputs into the recursion circuit, right? Because you're doing the
Yeah.
verification inside.
yeah. So the recursion circuit. Yeah. So in the recursion circuit, it takes as input each set as a witness and R charge R as an instance, and the gross 16 proof are the forwarding or gross 16 proof says, or the computation of this one is equal to the 0, or since in the gross 16 we can directly represent the equation as a constraint, we can
Oh,
just
this is
use the-
free. Oh,
yeah, yeah.
additions are free.
Yeah, so we can compute the inversion of this one,
Uh-huh.
and we can say, so we can use the same technique of the circom of the Israel template.
Mhm.
So it means.
Oh yeah.
So
Yeah, we're fine. We
then
don't need to do this.
our sim should be your first.
Oh, but asymptotically, that's going to be the same as this. I guess we skip this log p thing. We don't need this log p
Yeah,
thing.
so as a witness, it's recursion side computes the mass work, and I think the second template is its output is defined as our ZLLC.
Yeah.
So first it's defined as C, if it is not 0, it should be your ZRC inverse of that value, and if this is 0, it is 0.
Yep.
And I think it is defined as, and when this is actually, so I think or and so let me check the second wave difference. Yeah, but
We
anyway.
can just use is 0
Yeah,
basically.
it's a template for those examples.
Right. So we can skip the log p steps. But
Yeah,
we
yeah,
still
yes,
have to
yes,
do this.
Yes.
Oh wait, no, but we can also just do is 0 on each of these, right?
Yes, it's also possible. So we.
I think that is. Well, it just depends on the number of the multiplications. Because here you need to do.
Yeah.
You need to do 2n multiplications,
Yeah,
right?
yeah, yeah.
Because you need to compute all the r's. So
Yeah.
do r and then r squared, r to the n, and then you
Yeah.
also have to do these individual terms.
Yeah.
So it's 2n operation, 2n multiplications.
Yeah.
If this only has one multiplication, then just doing is 0 on each of them is better. If it has two, then they're equivalent.
Yeah, so I think it's the template has the two multiplication.
Okay, so
yeah.
then they're the same.
Yeah, so we can just output all that as
Yeah.
a public output in
Yeah.
the Singular and apply the is equation template on the recursion.
Yep.
Yeah, thank you very much.
Sounds
yeah.
good.
We can, yeah.
Math.
Yeah, math.
Solved.
Just